the early years of the 20th century, humanity was falling in love with the invisible. Radio waves crossed oceans, X-rays peered through flesh, and the atom, once a philosophical idea, started to feel like a real, measurable thing. But this romance with the unseen had a shadow, because tucked inside the atom was an energy so immense, so concentrated, that if someone ever learned how to unlock it, the world would never be the same. And the invention of nuclear weapons wasn't a single eureka moment. It was a chain reaction of discoveries, fears, moral choices, and wartime desperation, science sprinting faster than wisdom could keep up. It begins with curiosity, not cruelty. In the late 1800s, scientists were trying to understand matter at its most basic level. In 1896, Henri Becquerel discovered radioactivity almost by accident, when uranium salts fogged photographic plates without sunlight. Soon after, Marie and Pierre Curie pushed further, isolating radioactive elements like polonium and radium and revealing that atoms weren't solid, unchangeable beads. They were unstable, capable of transforming and releasing energy. That revelation was thrilling and terrifying. If atoms could decay, then the atom wasn't the end of the story. It was the beginning of something bigger, and potentially far more powerful. The early 1900s added more pieces. Ernest Rutherford, through his famous goldfoil experiment, showed that atoms had tiny, dense nuclei. Most of an atom was empty space, an idea that sounds poetic until you realize what it implies. If the nucleus is where the mass is concentrated, then the nucleus is where the deepest forces reside. Rutherford even managed to transmute elements, changing one type into another, proving that nuclear change wasn't myth, it was physics. And then came Albert Einstein's equation, published in 1905, E equals mc squared. A line of math that looked simple, almost elegant, but it carried a bombshell concept. Mass could be converted into energy. Even a tiny amount of mass, multiplied by the speed of light squared, meant an unimaginable amount of energy. People would later treat Einstein as the father of the atomic bomb, but the truth is more tragic. He provided a key idea, not a weapon. The weapon emerged when others discovered how to force the nucleus to give up that energy all at once. For decades, nuclear physics was still a frontier explored in laboratories, not on battlefields. Scientists fired particles into atoms, watched what came out, and tried to understand the rules. In 1932, James Chadwick discovered the neutron, electrically neutral, able to slip into the nucleus without being repelled by positive charge. The neutron became a perfect tool for nuclear experiments. That discovery mattered because it gave scientists a way to hit the nucleus like a silent battering ram. And once you can reliably strike the nucleus, you can start to imagine splitting it. Then, in the 1930s, the political world darkened. Fascism rose in Europe. Adolf Hitler came to power. Jewish scientists were pushed out, threatened, or forced to flee. A brilliant migration began. Some of the greatest minds in physics moved to Britain and the United States, carrying their knowledge and, soon, their fears. This matters because nuclear weapons were not just born from science. They were born from the fear that the wrong government might get there first. The bomb wasn't invented in a calm world. It was invented in a world that felt like it was burning. The turning point arrived in late 1938 in Germany, where chemists Otto Hahn and Fritz Strassmann bombarded uranium with neutrons and got surprising results, elements that were far lighter than uranium, like barium. Something didn't fit. The explanation came from physicist Lise Meitner, who had fled Nazi Germany because she was Jewish, and her nephew Otto Frisch. They realized the uranium nucleus wasn't simply absorbing neutrons, it was splitting apart. Frisch called this process fission, borrowing a word used in biology for cell division. But nuclear fission wasn't a gentle division. It was a violent rupture. When the nucleus split, it released energy, and crucially, it released additional neutrons. That last detail was everything. Because if each fission produced more neutrons, and those neutrons triggered more fission, then the process could multiply rapidly, explosively. A self-sustaining chain reaction wasn't just possible. It was inevitable, if you could arrange the right conditions. For scientists, this was awe-inspiring. For the world on the edge of war, it was horrifying. If a chain reaction could be controlled, it could produce power. If it could be made uncontrollable, it could produce a weapon unlike anything ever built. It wasn't just about a bigger bomb. It was about a different category of destruction, a blast created not by chemical reactions, like burning TNT, but by the energy binding the nucleus itself. In chemical explosions, atoms rearrange their electrons. In nuclear explosions, the nucleus changes. The difference in energy scale is enormous, like comparing a campfire to the sun. As war loomed, a terrifying question emerged. Could Nazi Germany build this first? Several scientists who understood the implications became alarmed. In 1939, physicists Leo Szilard and Eugene Wigner, both refugees, worried that Germany might pursue a bomb. They persuaded Albert Einstein to sign a letter warning US President Franklin D. Roosevelt that uranium could lead to extremely powerful bombs and that the United States should support research. Einstein's name carried weight, and the letter helped nudge the US government toward action. It's an emotionally complicated moment. Scientists, many of them pacifists or humanists, calling for the development of a weapon because they feared something worse if they didn't. It was not enthusiasm. It was dread. At first, the US response was cautious, but the pace changed as the war intensified and evidence suggested serious German research. By 1942, the effort became the Manhattan Project, an enormous, secret program to build an atomic bomb. It wasn't one lab or one genius. It was a massive industrial and scientific mobilization involving tens of thousands of people, spread across sites like Los Alamos in New Mexico, Oak Ridge in Tennessee, and Hanford in Washington. The scale was staggering. Factories built to enrich uranium, reactors built to produce plutonium, new instruments invented, new methods created, new materials developed, because the bomb wasn't just a theory. It was an engineering nightmare. Understanding how the bomb works means understanding the problem the Manhattan Project had to solve. Not all uranium is equally useful. Natural uranium is mostly uranium-238, with only a small fraction of uranium-235, the isotope that readily undergoes fission with slow neutrons. The challenge was to separate U-235 from U-238, even though chemically they're the same. Imagine trying to separate two identical sands, one slightly lighter than the other, grain by grain. That's what isotope separation felt like. Oak Ridge became a maze of technologies. Electromagnetic separation, gaseous diffusion, thermal diffusion, each complicated, expensive, and difficult. But the goal was clear: get enough U-235 to make a critical mass, the amount needed for a runaway chain reaction. Plutonium offered a different path. Plutonium-239 doesn't exist naturally in significant quantities, but it can be produced when uranium-238 absorbs neutrons in a nuclear reactor and transforms. That meant, build a reactor, produce plutonium, chemically separate it from the irradiated fuel. Hanford's reactors churned out plutonium on an industrial scale. But plutonium came with its own problem. It had impurities and a tendency to pre-detonate if used in a simple gun-type design. So the engineering challenge became even more intense. How do you assemble a supercritical mass fast enough that the chain reaction begins all at once, not prematurely? By 1945, Germany had been defeated, and the original fear, an immediate Nazi bomb, had faded. But the Manhattan Project did not stop. Now the target was Japan, and the urgency shifted to ending the war quickly, saving lives that would be lost in an invasion, and asserting overwhelming force. These were the justifications, debated then and still debated now. The truth is, once the machinery was built, once the bomb existed, it became almost impossible to imagine it not being used. That is one of the darkest lessons of technological power. Capability creates pressure. Having the weapon creates momentum to demonstrate it, to justify it, to end uncertainty with certainty, through a blast. On July 16, 1945, in the New Mexico desert, the first nuclear device was tested in the Trinity test. The device was an implosion bomb using plutonium. At 5:29 a.m., the desert lit up with an artificial sunrise. Witnesses described a flash brighter than anything they'd ever seen, followed by a rolling, crushing shockwave. The fireball rose, and then the mushroom cloud formed, the signature image that would become synonymous with nuclear terror. Scientists who had worked for years in quiet rooms suddenly faced the physical truth of what they had created. Some cheered. Some were silent. Some felt sick. Others recalled a line from the Bhagavad Gita: "Now I am become death, the destroyer of worlds." Whether he thought of it in the moment or later, the sentiment captured what it represented. Not just a test, but a threshold. Less than a month later, the threshold became reality for civilians. On August 6, 1945, the United States dropped a uranium gun-type bomb on Hiroshima. The bomb detonated above the city, releasing an immense blast, heat, and radiation. Buildings collapsed, people were vaporized, fires consumed and survivors suffered burns and injuries beyond comprehension. The scale was not merely military. It was human catastrophe. And then, on August 9th, 1945, Fat Man, a plutonium implosion bomb, was dropped on Nagasaki. Again, a city was ripped apart in seconds. Japan announced surrender soon. The Second World War ended, but a new era began. An era where humanity possessed the ability to destroy entire cities instantly and potentially end civilization. The invention of nuclear weapons didn't stop in 1945. It accelerated. The Soviet Union, understanding the strategic reality, raced to build its own bomb, aided in part by espionage and by the fact that physics is universal. In 1949, the USSR tested its first atomic bomb, ending the US monopoly and beginning the nuclear arms race. Then came the hydrogen bomb, or thermonuclear weapon, far more powerful than fission bombs, using fusion, the process that powers the sun. The destructive potential multiplied again. What began as a desperate wartime project became an ongoing global standoff, built on deterrence, the terrifying idea that the fear of mutual annihilation would prevent war. Peace by threat. Safety by hostage. It is a grim logic, but it shaped the second half of the 20th century.